So my name's Tyler. I'm data center SRE at Bloomberg. I'll try and kind of move through this quick since we're starting a little late. I called this presentation bare metal server discovery. You might have heard the term bare metal server provisioning. This is not installing an OS. It's something a little bit different. I hope you gain something from it. So Bloomberg uses almost exclusively, if not totally exclusively, a global private cloud infrastructure. So we don't use public services. We have data centers on the East Coast as well as small node sites throughout the globe. And we're also multi-architecture, multi-OS. So we have AIX, Solaris, X86. We run VMware. We run all kinds of operating systems. There's a lot of diversity. So what is bare metal server discovery? Bare metal server discovery, at least what we'll call it, is what happens when you bring a server into a data center. You have to introduce it into your environment. You have to baseline it. It has firmware, controller configs. You might want to create DHCP leases, introduce it into your IP address manager, all that kind of stuff. So this presents a unique challenge because we have so many different architectures, so many kinds of different servers, and so many different infrastructure teams that want to configure it in their own way. So some infrastructure teams have their own DHCP servers. They don't necessarily want leases. We can't get a consistent Pixie boot environment across the infrastructure. So there's a lot of challenges. And so this is really an operations problem. We're operations SREs. We want to be able to always have this work. So what we found is that the process changes a lot. People request new things. We have to basically keep agile. Somebody said yesterday in their presentation, infrastructure, nobody complains about infrastructure, or nobody comments about infrastructure unless something goes wrong. Nobody says, hey, you built me a great server. So what we found is that we have to be really flexible when we do this. And thankfully, right around the time when we started having these problems, a man named Gary Richmond came to Bloomberg to kind of enlighten us on Salt, and the rest is history. So before we get too far into how we discover servers, I'm not sure how familiar everyone is with what a BMC is. It's a little baseboard management controller. They're on every single enterprise server. It's usually just a little ARM CPU with some flash and its own RAM, and it connects to a ton of buses throughout the system. Your low pin count bus, your system management bus. It can talk to the NICs, it can get information about things. It has hardware monitoring, so it's monitoring the temperatures of your CPUs, and it's going to send out SNMP traps, it's going to have an event log. It can do a lot of things for you. It also allows you to control the power state of your server. You can pop up a virtual console. So for an operations guy, you want to jump on and debug the box without getting a crash card on it. It allows you to do that. And almost all of them are going to be accessible over the network. I mean, that's their purpose. It's a remote crash card. So they have various APIs. Probably the most common one that you'll see is IPMI. It's legacy, and it's pretty insecure. So a lot of them have their own custom APIs, or everyone's kind of starting to use Redfish. So it's a lot of XML, JSON. There's also some vendor-specific closed source proprietary binary APIs. But basically, this is what a BMC is, and this is what we can expect to see on every single server. And so what we did is we created a proxy minion infrastructure that works with all of 3 major X86 vendors. And there's nothing that prevents us from working with the rest of our infrastructure. We're scaling up and getting there, but this is where we are right now. So how our system actually looks is we have a host running a master, a host running several proxy minions. Those proxy minions then broker out to the actual management network and talk to the BMCs directly. And because Salt has different types of proxy minions, we can support basically different APIs, different vendors, and it's all neutral to us. We can test.ping everything, and that Salt takes care of broking out that command to that specific vendor's API. So our goals with the discovery were to be, one of them was to be entirely RESTful. We didn't want to rely on IPMI. We didn't want to rely on anything vendor specific if we don't have to. Why? Because HTTPS has much better ciphers than IPMI does. It's much more secure. It's where things are going. If you look at Redfish is a recent standard that's up and coming, that's much more reliable, it's much more easy to get status codes from it, and it's a lot better supported. So we also wanted to support all data center hardware. And as I mentioned, Redfish is up and coming. If you get a new server in 2018, it probably has it. But if you're supporting a server that's 4 or 5 years old, there's a good chance the vendor hasn't backported support. So we didn't want to say we can do this proxy minion thing and it only works with the brand new servers. We wanted to support everything. But we also wanted a rich feature set. So things like remote media, virtual CD, you can't guarantee it through IPMI. It's not part of the IPMI standard. So really you have 3 things, choose 2. You can't have your cake and eat it all. We did end up making some cuts in this and cutting corners, but we're working with vendors to work toward that RESTful goal as closely as possible. And honestly, we're almost there on X86. As I mentioned, we have support for 3 major X86 vendors. I don't want to list them just out of, I guess I don't want to sound like we're favoring any particular vendors. But the point being, we can really support anything with this approach. And we're looking at, as I said, we're looking at non-x86 servers in the near future. So we're looking at adding support for Solaris and AX as well. So the actual implementation. We started cracking open a proxy minion because that's really what we can guarantee on every server regardless of the environment. What we found is that really the proxy minion, if you look at the grains of a vanilla Salt minion, proxy minions have a lot of similarities. They both have DNS, MAC addresses, masters, all that kind of stuff. They have firmware releases. However, a BMC is a physical resource. It implies you have a server. That server has a location, it has a power draw, and other kinds of things. So if you use the compound grain matcher, you can generate some really interesting workflows because you can target a specific rack, a specific server, servers with specific power draws or anything like that. And basically, it's all done by the master. It's very efficient, and you can generate some really safe, neat workflows with it. So if I wanted to ping all of the servers in a particular cabinet, without even really thinking, I can just write this one line, and they're all going to respond. I'll know if or not a particular BMC in that cabinet is not responding. So when we implemented this, we faced a couple challenges, and we still do today. One of them being, how do you structure your proxy minions? You don't want to deal with the fact that APIs are different on all different kinds of vendors. You don't want to write separate workflows for every single time you add a new vendor. You want to write one workflow and have it work everywhere. So we tried to basically keep the interface of the proxy minion as simple as possible. You'll notice all the standard methods a proxy minion will have, but we have this special one called call. And all of call's, the only thing that call does is it basically provides durable command execution. So it's just going to make sure that that vendor's command works, and then we use basically a bunch of execution modules to give the illusion of method overloading. So we might implement get power state for each one as an execution module. So we'd have an execution module per vendor. All those execution modules support get power state. We know that if we call get power state on this minion, it's going to execute that command. And so that's how we basically wrote workflows around that. So one of the challenges with BMCs is that they're really unreliable. They will return random status codes, so you have to retry commands. We've even managed to basically expose some firmware bugs that will cause the BMCs to hang entirely. And the only fix is really to power drain them. That was across 2 vendors. We're working with vendors. We've gotten one of them to push a fix their upstream firmware today, actually. So this is still work in progress, but it's very promising. And as I mentioned, the BMCs will also return bad status codes. So a lot of them, if you execute a reboot command on the BMC, it'll just start saying you're unauthorized, or it'll give 500s for a little bit. So it's very tricky when you write the BMCs, and we found the best way to approach this was to have a Python module for each BMC outside of Salt that we can reuse. And that will worry about the retries and everything else. Another big challenge, how do you scale? So if you have a data center like Bloomberg, you're talking tens of thousands of servers. Every single server, you no longer have a minion for the host, you have a minion for the BMC as well. And maybe you have switches, so you have BMCs for those, vstrips, whatever you want to manage with a proxy minion. You have that many more BMCs. BMCs are really small ARM cores, so one of the things we did was we adjusted the keep alive interval. So normally, Salt will try and keep a persistent connection with your proxy modules if they support alive and ping. We had to bump that way up, just because we didn't want it to constantly be hitting the BMCs and making them write to their NAND and everything else. We also had to disable multiprocessing. So we found that we needed some state in some of the modules, like an IPMI session or an HTTPS session. And if you don't disable multiprocessing, it's going to keep creating more REST sessions. So we disabled it, and we used the same keep alive persistent HTTPS connection, and it helped us scale a lot better. The biggest one, probably outstanding today, in addition to scaling, is how do you provide fault tolerance? So if you think of a normal minion that you're running on a host, and the host crashes due to a hardware failure, ECC RAM, bad processor, the minion dying doesn't really matter, because at that point, the host is dead. However, if you remember our design from the original slide, we're running several proxy minions on a single host. So if that host dies, host B dies, all those proxy minions are going to go with it. So how do you account for that? We thought of a couple solutions, and we're still looking at a third one. One of the ideas was just leverage the fault tolerance of Kubernetes. Put all those proxy minions in a pod, and if the hardware dies, those proxy minions should spin up a new pod in some amount of time. Solution 2 was to utilize a runner. So the other idea was you have multiple proxy minions running. They have different minion IDs, one's A and one's B, and the runner determines which one's alive and routes the connection to that one. However, it's not very Salt-like, it's not simple. You now have a runner, it might mess up your targeting. So we don't really like that one either. We're more heading towards solution 1, but it's something to think about if you want your proxy minion to always be there. If you're going to provide this as a Salt API that other people are going to use, you have to think of the fact that host B may just die. So on day 1, we weren't confident enough to just start churning up thousands and thousands of minions. The BMCs are, like I said, they're really unreliable, and they control the power state of your servers. So we didn't want to start, bricking a lot of our infrastructure. So what we actually found is that Salt is really easy to hack on. If you go open up something like even Salt Minion or Salt Master, you'll see that it really gracefully starts calling into the APIs, and it's really simple to use. So what we did was we created a tool. I actually called it Pepper, because before I knew that there was a SaltStack Pepper, we thought it was a catchy name. So basically the lesson learned was don't be afraid to break past some of the documentation. Feel free to look at the API, and we still actually use this today. It's still one of the tools that we rely on. When we have a workflow to run in a BMC, we basically just spin up a proxy minion on demand, run the workflow, and then shut it back down. And that way we don't have to have tens of thousands of these running if we don't want to. So enough about the design. How is this useful? How can this help me? So there's a CVE that was actually released somewhat recently. Well, they're not batted, so you're not providing anyone direct access to the BMC. You're providing them direct access to the Salt API. And the Salt API is never going to write a header like this. So going back to that targeting, just like we can target a physical part of our infrastructure, we can target certain minions using grains. So in this case, we're basically saying, go find a list of all of the BMCs that are by this vendor with this firmware version and just see which ones are pingable. Give me a list in JSON, and then we just use a simple JQ filter to basically pull out the ones that are pingable. So we know these are basically responsive, vulnerable hosts. And then with the second command, using REST and Salt, we can actually upload the firmware to those BMCs. And we can use Salt's features like batch size to slowly roll it out and get an asynchronous job. And if it starts causing a problem on our infrastructure, we can just cancel that job before it causes too much problem. So it's a really neat feature of how to leverage Salt tools to secure your infrastructure, especially thinking about the SecOps. And the neat thing about this is that it truly extends to BIOS. So especially in a place like Bloomberg, people are running market tickers and things with very little latency. We can't run a Salt minion on everything because some people are working with microseconds of latency. Just the fact that a Salt minion starts up and that process context gets switched in would ruin it for them. So you want to make sure that all of your infrastructure is protected against attacks like Spectre and Meltdown, even if you don't have access to that OS or that person's not willing to run a minion on their box. You can do this using the BMCs in the same way that I just demonstrated. You can protect the BMC, you can protect the BIOS. And I think this is going to be something that's really important for the foreseeable future with all the speculative execution attacks we've had, Meltdown, Foreshadow, Spectre, and all its variants. And the lovely thing about it is no OS is required. The box could be off, it could be waiting to be provisioned, it could be in production, running something, and it will actually stage the BIOS firmware the next time the host reboots. So all you have to do is just put the BIOS in the BMC, tell the person just reboot the host when you want it to kick in, and boom, like that, you're secured. So this goes back to, now that I've kind of covered the proxy minion architecture, this gets into the really interesting part. As an operations SRE, a lot of people just tell you, just PXE boot a server. You'll read online, and people say, oh, you can just PXE boot it to our provisioning image. Like I said, for various reasons of our network, various reasons of you get a brand new server, something's broken, or maybe the port's not configured right. I'll go over all the things that we see, but basically, PXE booting works really well as long as it's been PXE booted once before. The first time you have to PXE boot, you can run into all kinds of problems with new infrastructure. Anyone who has ever turned on a server, or even their host at home, and tried to boot it, you might have seen this message before. It's incredibly unhelpful. That message will be returned for literally any cause. And you sit there, press a key, maybe if you're lucky, the next 5 minutes, the port will flap again. On the switch, you'll get a MAC address for like 5 seconds, and then you lose it. And it's back to where you started. How do you debug something like this? I mean, you can get a live CD, stick it in, and troubleshoot each one, but that's a huge time sink. Just check the cables. And no, this is not a Bloomberg data center, but this is actually a data center in New York City that is managed by a totally separate company to give you an idea of how hard this can be to troubleshoot on some infrastructure. So going back to what kind of problems have we seen, right? You can have cabling and SFP issues. So if you use fiber is a very short bend radius. It can snap easy. You can have the wrong polarity. You can have weak light levels. Your SFP can be broken. I mean, the old adage for electronics is true for servers. If it's going to break, it breaks in the first 2 weeks. So you'll see a lot of stuff just broken when it comes in sometimes. Access switches can be misconfigured. Maybe somebody's automation breaks and the access port is just not configured, and the port is just not going up for that reason. We've seen code bugs. So in link aggregation, one side will stay down. We've seen routing and firewall issues. So if your firewall is blocking the server's ability to either get a DHCP lease or reach a TFTP server, it's another problem. You can have multiple authoritative DHCP servers responding, which is really head scratcher. All kinds of problems. And then the last thing we'll see, this one's fixable by Salt for the most part, at least for the BIOS, but you have to make sure the boot order is correct. With UEFI, you have to make sure that the NIC option ROM driver actually loads. Some BIOSes give you the option to disable it, and we've seen it disabled by default. So how did we tackle this problem without spending a ton of operations? We simply leveraged the BMC. We used the BMC to basically boot the server to a provisioning ready image. It's really no different than booting a live CD, but we can do it all through the BMC, and it's all totally automated, and it works everywhere because it's just using the BMC. So we leverage the virtual media to load a kernel image and an intrd, and we can get basically the full advantage of Linux 4.19 right now with all of the hardware checking and driver support and everything that comes along with it. And so once the server boots, it actually utilizes the BMC's virtual serial port as its means for communication. So your network doesn't even have to be up. As long as the copper cable is ported to the BMC, you have a communication vector. Basically, dev TTY is 0 on the host end and the IPMI serial port on the other end. And we just talk over that thing. We just basically send JSON messages over it. So how do you provision? Really simple. Server starts powered off. You mount a virtual CD into the server's drive. It's usually just exposed as a USB CD drive. You set a option saying boot off the CD for the next boot only. And then we have a thread that once we power on the server is looking for a certain message on the event bus. And we kick off a thread and make it watch that. Once Linux boots, systemd starts up and starts broadcasting that message on the serial port. So all of a sudden, that event then triggers a reactor that we can go and start provisioning that host because we know Linux is up, when we know that the serial port is going to be responsive to our command packets. So this was really interesting because with the BMC, one of the things that's really frustrating is you get different vendors supporting different features. Some will let you see the MAC address of the NICs, some won't. Some will let you see processor and DIMM information, some won't. Some will let you see NVMEs, some won't. So what we can do is basically just leverage Linux. It'll show us everything. We can get serial numbers and firmware and model numbers, and we can basically build an agnostic hardware profile of that server. So to give you an idea of what it actually looks like, we gather all this information in the daemon running on the host from the SM BIOS. We can even get like the serial number of the transceivers we wanted to, light levels, which has actually come in handy before. If you get a bad batch of transceivers and you want to go look back at some returner information to see which of your hosts are affected in your infrastructure, we can do all kinds of neat things like this. And it requires nothing, it assumes nothing about what's on the host. So we can also use it as a troubleshooting tool because it doesn't affect the state of the host. We're just booting this over the BMC. As long as that OS is down, we can do this at any time. So enough about the actual workflow. How do we use Salt? So if you've used AWS, you're familiar with all the different flavors. You can get x2.large, mini. I'm not sure what they're called, but we have a similar concept with hardware. So we have flavors of hardware. And what we do is we actually use that information that we grab from the host and map it back to a flavor. So on any host, I can just basically define this in my pillar for the flavor, start up the host, and tell it to basically identify itself. And it says, oh, I'm this flavor. I'm a 2017.c, which is really useful because you can pick out hardware errors with this. If a storage controller doesn't enumerate, it's going to say, oh, gee, I don't know what that is. And then you can have somebody go look at it, or you can look at the hardware logs to figure out why all the hardware is not showing up, or maybe you're introducing something foreign into your environment and you want to know what it is. One of the most useful pieces, though, is the ability to validate the physical network interfaces. So even if the ports are misconfigured, most of the time you're still going to get LLDP information. So that this is actually a response of part of what Salt sees. It's the actual return dictionary. But you can see on the top, the first dictionary, it's a little bit Bloomberg speak, I guess. But you're looking at slot 1 and 2 of the card and port 1 on both those slots. And then it breaks out into a standard breakout cable. So we can actually compare this to what BDMS, which is the Bloomberg Data Center Management System, it's basically our asset system, what it says is supposed to be, and what cables were actually supposed to be run per the work order. And so we can use Salt to validate that what actually is connected is what we wanted. And we can do this at any time. Just go make sure a box is cabled right. And if it's not, like in this case, I've colored it in red, at least the part that's not. It's very clear to an operations engineer exactly what's wrong. And you don't have to troubleshoot a network issue. You know it's layer 1. You can just go fix it. So it's not just NICs. We do something similar with HBAs. So in this case, okay, something's wrong with slot 1 HBA. So I can go take a peek at that, open a case with the vendor, and go have that looked at. And it's not, this is all totally automated. I don't have to mess around with the host or run commands on it or look at it myself. Getting in some other things that we can do. We can flash and configure various controllers. So we have salt states that will call tools on the host that maybe with the BMC you can't flash that firmware. But because we have Linux, because we have the host and we have this interface, we can basically go make sure that the NICs are flashed with the version that we want and that the ports are configured for Pixie Boot. We don't have to worry about things like that. So similar, we can also manage the firmware. You probably want to do this using a map file. It's definitely not the most elegant way to do it, but it all fits in one slide, so it's pretty nice. We have different groups who will mandate different firmware versions. And ordinarily, that's a problem. You have to have a matrix somewhere to maintain it. But in this case, we just tell Salt, just boot the machine and flash it with the firmware that you expect. And this is something that's really useful for after hardware replacement. So you get a NIC replaced because it dies. And then you just tell the operations team, hey, just run this utility. It's gonna run a Salt high state, and it's gonna provision it with the right firmware and make sure that everything on the box is exactly consistent. So we also have orchestrated provisioning. So after we got this whole high state of the actual firmware and the controller config that we can run on any part of our infrastructure, we actually started tying it into our internal ticketing systems. So normally how it used to work is our group would get a ticket saying stand up this rack or stand up this box. And we would boot it up, make sure that it had the right firmware, that the controllers were configured right. Now we just look at that ticket. We take some attributes out of that ticket, look it up in the asset system to figure out if it's a cabinet, which servers we're targeting. And then we just boot those servers and just run this high state. And it's all totally automated. It's awesome when you get an email in the middle of the night telling you that your automation just configured a rack. So we're continually going forward with this. As I mentioned, we're working on different vendors. We're working on Solaris and AIX and those things as time permits. Some of the other things we're looking at doing is Foreman discovery automation. So we use Foreman as one of our provisioning systems. If you're not familiar with it, I think it's a Rail project. Basically, it just takes a bunch of facts and uploads it to a provisioning server. And that way, an admin can just basically click build, and they can select our operating system that they would like to build. And the box self-discovers itself. So it'll actually it's a command and control server of sorts, and it will give it a kexec command to boot into a certain Anaconda and uninstaller and just provision the box for us. And meanwhile, we can basically have this box in an environment with a full kernel booted that an engineer can just look at, as opposed to a Pixie boot that has all these problems, and we can control the actual environment that it's sitting in while it's waiting to be provisioned. And we have all the tools, the firmware, everything we need to debug it. We're also looking at getting DHCP leases and assigning A records and C names using our IP address manager. Just make a little more easy on ourselves. We are, like I said, we're constantly building up the system. Better automated troubleshooting. So we have tools like Tshark, traceroute, ping. We'd like to be able to automatically address some of these network and routing issues using more Linux tools. And the last thing we're also focusing on is hardware monitoring. So a server is going to break in the first few weeks, and you can basically just look at the hardware. Look at the hardware for error logs while it's waiting for provisioning. And if something calls out that the BMC doesn't catch, which is common for NVMe drives and stuff, you now have a log of it. And you can occasionally stress test the hardware as it's waiting to be provisioned. So in summary, I hope what you took away is that we often use Salt as an OS configuration management tool, but it's so much more than that. You can create and automate workflows that work on hardware, asset systems, ticketing systems. and go well beyond the scope of just an OS system. Proxy minions are a great way to manage your infrastructure. So there's already some napalm stuff out there to manage switches. We just introduced some BMC proxy minions, and regardless of how the tenants are using that architecture, you're targeting an out-of-band device that's on every single piece of physical infrastructure. So you're always guaranteed to be able to basically use Salt and configuration management against that hardware. And then the last thing, don't be afraid to go beyond the barriers. So, execution modules, state modules, all that stuff. Salt has so much to offer. Look at the engines, look at the inside of the source code, and see all the cool things that you can do with it. That's it. We're hiring. There's our career site. Our specific team is actually hiring. If you found this particular presentation interesting, I put up the requisition number up there just in case you wanted to take a peek at our specific team. But yeah, that's it, and I open the floor for questions. Thank you. Yep.
Are these BMC proxy minions going to be upstream installed?
So the question was, are these BMC proxy minions going to be upstreamed, open sourced? It's something we'll have to, I actually anticipated this question. It's something I'll have to go back to legal and our team and everyone at Bloomberg and look with. One thing I will note is that we do have several Python modules that we've also developed that are prerequisites for the proxy minions. And the proxy minions are not very much, but somewhat ingrained into our asset inventory system. So when it starts up, it'll read the serial number off the device, and then it will go straight to the asset system to figure out where that device is physically located. So stuff like that we would have to somehow gate or take out. But I will go back and look at the possibility of it.
From looking back at last year's SaltStack, there was a keynote by John and from Bloomberg. And basically, this is the extension of kind of some of the stuff you mentioned.
Yeah, so he spoke, I guess, probably more from our core automation side. So this is just like our pre-provisioning environment for Salt. Once the OS is installed in the box, it's depending on the infrastructure group that manages that particular host, they may or may not install a minion. I mean, most of our infrastructure does have minions, but that he was speaking more to the OS installation, the post-installation management, patches, all that stuff once the OS is provisioned. Yep.
Talking to your kind of pre-install OS with serial number sounds great. Novel idea. Can you talk a little more about how exactly that works? Is it sort of spec style something that's in demand? What's going on?
So the question was, can you explain a little bit about how the virtual serial console works? It is just JSON messages being blasted across the serial line. There's like a heartbeat and stuff. I kind of just created the protocol on the fly. It's not perfect. I would say it has at least 90 to 95% reliability, and we're constantly making that better. One thing that does make it difficult is, like when we were initially prototyping this, we did it for the data center on the East Coast. And then we started going out to the rest of the globe, and we're in like China where we have like half a millisecond of latency from the States, and we didn't have a Salt master there yet. So we ran into problems with like flow control. So if you do decide to do this, pay attention to flow control, parity, make sure that's all set up, test it outside of Python. But once you have those things, you pretty much have durable message transfer. So we just really used a really simple JSON scheme with it. It's easy for the daemon to process on the other end and easy for us to add in commands.
What do you do when you get locked out of the power drain? Do you guys have that automated use and stuff, or is that a physical?
No, we absolutely do not power drain a server. Well, for their automation, that's always going to be a human, just because it's not a risk that we want to take. But we basically, yeah, we found all those bugs, and we work with it. Well, they're actually, those kinds of bugs aren't too common. I can think of in my head, and one just got patched into an upstream firmware that a vendor's now has released, so that's gotten fixed. Using the debug logging, it's pretty easy to get a reproducible series of steps. So if you see a host hang, just go look at its debug log, see what was run recently, try and just replay those same states with those same arguments, and that's how we actually found this last one. Somebody noticed that whenever they ran this particular workflow, that it would always hang the BMC. So we just basically played over those same series of commands. It hung, went to the vendor with a very reproducible steps of commands, and they had it triaged in pretty quick. Sure.
Is everything that you guys do with this always when there's no OS running? Or, I mean, a thought came to mind, if you have an OS running and it hangs, you could probably reset it and reset the OS.
So the command, the question was, do we always do this when an OS is running? Right now, this is honestly pretty exclusively used for this workflow. It does do some other things, but we are working with the rest of the infrastructure group at Bloomberg to make this API accessible so that it can be way more than just a discovery system. It can be used to, as a vector for powering off on and off servers, and doing whatever other kinds of things you want with the BMC, whether it be flashing the firmware when the host, to do something like flash the firmware or the BMC, you don't have to have it booted to the, our OS. It can be booted anywhere. You can just do it that way. So definitely more usage than just this particular use case. One more question. So how do we bootstrap the discovery of the BMCs? We watch a list of DHCP offers within particular subnets, and once they're up, most BMC vendors have a default set of credentials that we can log into, pull it into our asset system, and relate to an entry in the asset system, or ticket on that event. I think that's it. Well, have a good SaltConf.